One of them to design a unit, and the other one is to rate a unit or look at the performance of an existing unit. Design the unit, you are going to use figures, like what you have in the first and second problems of the last homework. Then we have figures that are ready. We have basically 3 figures. One of them is for gain output ratio. The second figure is for recovery ratio. And the third figure is going to be for, anybody remembers?
Mass ratio.
Mass flow rate. Yes, mass flow rate ratio. So basically, these figures are having an x-axis, which is the effectiveness. I'm not quite sure whether the effectiveness of humidifier or dehumidifier. And the other one is the effectiveness of the other component. So one is the effectiveness of the humidifier, one of the effectiveness of the dehumidifier. So the problem should have the values of the effectiveness for humidifier and dehumidifier given to you. And accordingly, you would be able to know if you are given the distillate flow rate, which is always the case. I mean, we say that we need to design an HDH system that can provide us with the problem in the homework was saying 1 cubic meter per day. أنا محتاج طن من المية الحلوة كل يوم. I would convert that into kilograms per second, and then that becomes our productivity. Then, when I'm calculating based on this epsilon, I calculate the GOR. Again, the GOR, as we mentioned before, this is m dot distillate into HFG divided by QA. HFG is a constant value. So normally, we take it something like 2330 or 2350 or whatever kilojoule per kilogram. So if I know m dot distillate, I know HFG, I know the GOR from the figure, I can get QA. Recovery ratio is m dot distillate that we have divided by m dot seawater n. The distillate quantity is known. The figure gives me the recovery ratio, then I can get m dot seawater. MR is m dot seawater divided by m dot air. So if I know the value of MR, I know the value of seawater that I got from the previous step, then from here I can get the mass flow rate of the air. So this is basically the case, whether we are talking about a water heating or an air heating system. The water heating system has its own figures. The air heating system has its own figures. And then basically, this is how we get the basic components. And there will be another parameter if I need to calculate, for example, the surface cross-sectional area of the humidifier. Then we use m dot water over area as the mass flux in the humidifier, and we pick a value of 1.5. You can pick a value between 2 to 4. It's all up to you, but it's just we agreed that this is a reasonable selection. And then I would know the value of m dot water from here, m dot seawater, which is here, I know it. And this is a constant, so I can get the cross-sectional area of the humidifier. So this is how we determine the dimension. And then we go to another figure that is going to give me the height of the packing material based on the maximum temperature, which basically, because these figures were made for a maximum temperature of 60, so in most of the cases, you'll be asked to deal with it for a case of maximum temperature of 60. If the maximum temperature of the system is different, then we have to provide you with the figures that are suitable for that. Then you calculate the height of the humidifier. Then there's another equation based on the overall heat transfer coefficient, which is given to you. You can calculate what is the surface area for the dehumidifier, whether it is based on water heating or air heating, and then you can get the value. So we're talking about some sort of standard steps that you are going to follow in order to do a thermal design of the unit. differences here. I mean, I can expect when I'm asking you to come up with a design for an HDH system that I would have results that are not similar, because there's a human factor when you get a value here and a value of the figure, and this value somebody can calculate the GOR as 1.9, another one calculated as 1.95, 2 or 1.8, something like that is acceptable as a tolerance in the solution. So I don't expect, and you are not requested to provide an exact number, because that's something, for example, somebody have a figure like this, and you got the point of intersection here, and you need to move to the left. Somebody would do it like that. Somebody is going to do the left is like this, the left is like that. So, or each one of them, somebody would consider it visually as a horizontal line. So that's the kind of, based on the scale that we have. So this kind of variations that can be expected in a system like that. What is more important is how you are following the procedure for the analysis.
Doctor?
Yes.
Yeah, so for the surface area of the, I believe there is a figure to find out, to calculate the, or to approximate the surface area. Is it for the humidifier or for the dehumidifier?
It is for the dehumidifier. Surface area, then it's for the dehumidifier. The humidifier, you have to calculate the cross-sectional area and the height of the packing material. That's all. We cannot do more about this.
So 1.5 represents the height of the material, right?
No, 1.5 represents what we call the mass flux.
Mass flux.
The mass flow rate divided by the cross-sectional area.
I see.
This number came from the analysis of the cooling towers. You use this to calculate the surface area. But the height, this is something else. It is based on the effectiveness that you have. It is based on the temperatures that you have. And you can see what is the best height of the packing material. There's a figure for that. But there's no figure for the area. We use that expression.
All right, thank you.
You're welcome. Now, the second kind of problems that you can have dealing with HDH systems is the rating problems. You have an existing problem and you need to do an analysis of the performance. In that case, Muhammad Al-Gham, do you have a question?
Yes, Doctor. What about the formula that NTU equal U A surface over C minimum?
It's another way to calculate the surface area. So the surface area can be calculated from a figure right away, or can be calculated based on the number of transfer units and the specific heat ratio, which is the capacitance ratio. You can do this or that. It's easier to do it directly as area of the dehumidifier based on this. Otherwise, the number of transfer unit is an overall heat transfer coefficient multiplied by the area divided by C min. What is C min? This is basically M dot Cp minimum. We have two fluids. We have water and air. You calculate M dot Cp for the water, M dot Cp for the air, and you take the lower value. This is your C min. The overall heat transfer coefficient would be given to you. The number of transfer units, you can get it from the figure, then you can calculate the area.
So you will be, if the figure is not given, I can use this formula and we'll get same number.
Yes, it's basically given the same number, but normally the value of the overall heat transfer coefficient is given to you because calculating it is a little bit involved, that you have to go for forced convection inside the tubes and a kind of condensation on the outside surface of the tube. So the correlations, it would be some sort of a lengthy process, which is not the target. The target is to come up of how to calculate the surface area. That's something probably you can ask in a project, that you can calculate the details of the overall heat transfer coefficient. Did I answer your question, Salah?
Yes, Muhammad.
The thing here which would be considered is when I'm talking about a rating problem. Rating, it means that I do have the components, a dehumidifier and a heater. And the information will be given to you in a way, like what you have seen in the quiz, that needed values of the enthalpies are always given. I'm not going to ask you to go for the psychometric chart or even go to the existing softwares on the internet to calculate H for humid system, for humid air. That will be given to you always. What you would be expected to do is to be able to run the energy balance and mass balance, of course, for the system. The only mass balance that we would have, now I'm talking about a water heated system, is that m dot water coming to the humidifier is going to be basically m dot brine plus vapor, which will be carried by the air. So the kind of mass balance that we have here is that m dot water entering will be m dot brine rejected plus m dot evaporated. Sorry. The m dot evaporated is going to be the quantity of water vapor carried by the air, which is m dot air into the difference of omega between points 2 and point 1. So we have here air coming in at state number 1 and air leaving at state number 2. So omega 2 minus omega 1 is the difference in humidity of the air, and this is basically the quantity of water vapor carried by the air that's going to define m dot evaporated. So this is the mass balance equation. Other than that, the equations that would be required are basically the energy balance, and the effectiveness expression. Energy balance, if I'm talking about a humidifier, then let's look at the components. We have air coming in, so m dot air into H1. We have water coming in, m dot water, H water. Let's call this 3. This is the energy in. The energy out is going to be m dot air, H air 2, and m dot water, H brine. And I have to tell you here that whenever we are talking about water, it is an acceptable approximation to put this H as Cp into temperature. It is not very accurate because the way Cp into temperature has been basically created for a difference of energy, like delta H, for example, is m dot Cp delta T. But the expression of Cp into the temperature can approximately be accepted as a way to represent the energy of the water, provided that you are sitting in an exam and you don't have softwares that you are going to, or table that you put the value of the temperature and it will give you the enthalpy or vice versa. So Cp into T can be acceptable then. This is the energy out and this is the energy in. So this is the energy balance for the humidifier. As I said, always the values of H will be given to you. Sometimes we hide one of these values of the H's. It is not given and you are asked to calculate it. Asking to calculate it, which means that you are going to deal with the effectiveness expression. And we have effectiveness based on the water side or the air side. If you noticed in the quiz that I've specified that this is effectiveness of the air side so that you don't have to write both of them and search which one is the highest because some of them will not be given. So when I'm saying, for example, effectiveness, you are given effectiveness for the air side for the humidifier, then this is basically going to be H air outlet minus H air inlet divided by H air outlet ideal. So let me put it this way, H air ideal minus H air 1. H air ideal, this is the ideal condition for the enthalpy of air. as if air is being heated here to the maximum temperature, which is this. So this is basically H of air at a temperature equal to T water 3. And this is also given to you. So if the effectiveness is given and this value is given, HA1 is given, then I can ask for the value of H2, which you can obtain it easily here, which is for the air leaving the humidifier and going into the dehumidifier. The same thing can be done. If, for example, I can probably not provide you with the T water leaving here, but rather I would ask you to calculate this value. Maybe you can calculate H water out from here and then substitute into this equation to get H of the brine. So that's something that can be done in problems. So that each time in one equation, you have only one unknown. What I want to make sure here, or to make it clear, is that you are always be having an equation, and the equation is going to have only one unknown. The effectiveness expression here, you can use this expression to get enthalpy of the air leaving the unit. Then make use of the enthalpy expression here to substitute it into the energy balance and calculate, for example, what is the enthalpy of brine leaving. What about the quantity of brine? If here that, to be more accurate, this is m dot brine, and m dot brine is going to be m dot water, which is always given, minus m dot evaporated. What's m dot evaporated? It is m air into the difference in omega. So this is as far as the balance or the energy balance for the humidifier is made. If I want to look at the other component, yes, ya Khalid?
Yes, Doctor. A question here. If would it be the formula for the effectiveness, whether it's for the humidifier or the dehumidifier, be different?
I'm going to that. Yes, I'll be talking about this in a while.
If we change the system, like open water, closed water, that's all.
Actually, when it is open water or closed water, that does not make a difference in the effectiveness expression. Values would be different, yes, but the effectiveness is what? Is not. The point here is, now I'm talking about m dot evaporated. Is the m dot evaporated as the same as m dot distillate?
Yes.
It would be if it's a closed air system. If it's not a closed air system, then it's not. And probably the problem, is it the problem of the homework that you have an open air system in which you have the two units here. Here air is coming from outside. So it has its own enthalpy. And this is the air when it's humidified, it's going to enter, which is in H air 2. And what we have here, air, it's not a closed loop, but we are throwing the air away. So m dot evaporator here is going to be m dot air into omega 2 minus omega 1. But m dot distillate is the difference here across this unit. So it will be m dot air into omega 2 minus omega 3. So this value and this value are not the same. It's not a closed loop of the air. You are extracting air from the atmosphere and you are throwing air to the atmosphere, and it's not a closed loop. In that case, the condition of omega 1 and omega 3 are not the same. So this is what you need to be aware of while you are looking at the problem. Am I talking about a closed air system cycle or an open air cycle? I hope I did answer your question, Khaled.
Yes, Doctor. But again, you said there is no difference if it's for the effectiveness.
There's no difference in the expression of the effectiveness. As long as I'm talking about water heating cycle, and the water enters here hot, and the air enters as cold, then the effectiveness is not going to change, whether it is an open system for the air or closed system for the air. Water is hot and air is cold. So always the effectiveness is going to be this expression here.
How about the heating system? If we change it from water heated to air heated, would
Yeah,
the expression be
this
different?
is going to make a difference here. When I'm talking about a humidifier of an air heated system, then that's a little bit different. Why? Because the hot fluid is the air and the cold fluid is the water here. So let's put this in which I'm using air and the air is passing by a heater inside. And this is air 1. And then it will leave here as air 2. And it will enter to the dehumidifier and leave it as air 3. Again, the value of the evaporated value versus the condensed values are not the same, because this is omega 2, this is omega 1, and this is omega 3. And when I'm looking at the effectiveness of the humidifier here, the natural difference is basically going to be H air 2 minus H air 1. What about the maximum difference? The air, what happens to the air here? Is it heated or cooled down?
Cool down.
It is cooled down because water is colder. So air will be cooled down, which means that actually the way I should put that equation, actually this should have been H1 minus H2, because air comes as hot and it will leave as a cold value. Then this air is entering at H air 1. This is coming from the heater, so this is not going to change. But the humidifier is going to cool down the air. What is the lowest temperature that the air will be cooled down to?
Water inlet.
Water inlet, which will be this. So this is H air at water inlet. Definitely when water is sprayed, water is going to be taking some energy from the air and it will leave here as m dot brine at T brine, and T brine is going to be greater than T2. Because basically air is hot in this case. So that would be how I write the expression of the effectiveness. Again, when you're looking at the effectiveness, you are looking at the actual enthalpy difference of the fluid that you are considering divided by the maximum difference. If the air is being heated, I look for what is the maximum temperature in the condition in the unit here, and I'm going to consider the enthalpy of air there. If air is being cooled down, I'm going to look at what is the minimum temperature here, where air ideally is going to be cooled down from its maximum value at the inlet to the lowest value, which is this. So that in the denominator for this one and this one, basically what I'm looking for is delta H maximum. Okay.
All right.
Now, let's look at the dehumidifier. And for the dehumidifier, I'm going to write, again, the mass balance and the energy balance, and then the expression of the effectiveness. And again, you might be given the value of the effectiveness, then you are going to make use of it to calculate some sort of an enthalpy. The other enthalpy that needs to be calculated is going to be calculated from the energy balance. So always, you're going to have your system in a way that you have only one unknown per step. So now let's consider the dehumidifier. It is receiving air at 2, returning air at 1, and then this is water here coming as water 1, leaving water 2, and this is water 3. And there is distillate which is leaving here. Now, the effectiveness of the dehumidifier in the air side, actual actual difference in enthalpy, which is H air 2 minus H air 1. If it's an open system, it will be H air 2 minus H air 3, which is the actual difference of enthalpy across the dehumidifier divided by delta H maximum. H air 2 here is coming with a certain known value, which is what is going to happen here? Air is going to be cooled down, so it will be the inlet condition as is, and air is going to be cooled to the lowest temperature, if I'm talking about 100% ideal situation, which is the inlet water temperature. So this is going to be H air at T water 1. So this is going to be the effectiveness expression. If I'm looking for the energy balance, then the way I prefer it also is the energy N, which is m dot air, H air 2. Water is entering, so have m dot water, H water 1. This is what comes into the unit, to the dehumidifier. What leaves the humidifier is m dot air, H air 1 if it's a closed system, and H air 3 if it's an open system, plus m dot water, H water 2. Water has heated a little bit by gaining energy from the condensing air. And there is distillate which is leaving, H distillate. Normally the value of H distillate will be given to you, unless this is what we are looking for. You are given all the values and we need the value of HD. But otherwise, the H distillate would be given to you. And the m dot distillate is going to be basically m dot air into the difference of omega across the units. So it will be omega 2 minus omega 1 for a closed system, omega 2 minus omega 3 for an open air system. So problems related to the HDH in terms of rating will be something similar to what I've shown here. The only difference that I did not talk about is going to be in case of we have air heating after it leaves the humidifier, which is the modified air heating cycle. And for this cycle, there is some difference here, that a piece of information that we don't give to you because we assume that you should know it. And that normally becomes, in some cases, the trick of the problem, which is the kind of heating that happens in an air heater is sensible heating, which means that I think the problem that we have, so the example that we have solved in class was of that kind. I'm talking about a humidifier, and then a heater, an air heater. So the air is being heated here. So this is air at state 2. And then this is leaving at air at state 3, which is at a higher temperature. And this is the humidifier. This is the dehumidifier. And then the air gets back here if I'm talking about a closed system. Water is going to enter here, water 1. Water 2 is going to enter here. And here we have the brine rejected, or water 3, if you want to call it this way. So what would happen here is that across the heater, heating is sensible heating only. Remember that. Which means that omega 2 and omega 3 are the same. This is a key for solving this problem. That the mass of the water vapor carried by the air did not change. I heated it, but I did not add by condensation. I did not take something out by evaporation. This is only sensible heating for the air. Definitely phi is not. Because phi is a function of omega and temperature, and the temperature definitely is different. But the key for solving this kind of equation of modified air heating is that across the air heater, the value of omega is constant. It is not changing. So when you find you have a problem like this, I may give you the value of omega-2 and would not mention anything about omega-3 and probably tell you here that we're going to heat it to a value of Tmax equal to maybe 80 degrees centigrade. When you look at the problem statement, you'll find that at state number 3, you are having only one property, which is basically not enough. But this is made based on that you would know that the value of omega across the heater is constant and it is not changing. So this is basically the kind of tricks that you can see in an HDH problem. I'm afraid the time has already ended and we don't have time to talk about the single effect evaporation, but we have already gone through an example for the single effect evaporation. Right now, after the class, I'm going to post the book of Ed-Dessouky and Ed-Touni on saltwater desalination. And you'll find in that book that chapter 2 is dedicated to single effect evaporation. It has example and it has end of the chapter, maybe a kind of 3 or 4 problems that if you need to practice on that, you can do that.
All right. Thank you so much, Doctor, for that effective revision.
Doctor, the time for the midterm.
Oh, yes, I'm glad that you brought this point up. There's one suggestion that we can start in the class time so that you can make use of the early morning while you are fresh. If you all agree on that, which is fine with me, then, but we have to log in, not 8:30, but we have to log in at 8 o'clock because we need to make sure that I will just take the attendance properly. You are going to adjust the cameras and I make sure that everyone of you is having the right position of the camera. I sent you an email at the end of our last quiz indicating who's having a good posture position of the camera and who have something hidden. So that I want you to follow what is the best technique over there. So to make sure of that, we'll need this first 30 minutes to make adjustments for the setting. So if it's fine with you to start at 8, so that our quiz is going to start at whenever we are ready, 8:15, 8:20, 8:30, and it will be for 1.5 hours. It will be 3 problems, one on the solar still, one on the HDH system, and one on the single effect evaporation. If it's fine, whoever is agreeing on that, you can please check yes, which is down there below your names. Anybody has a problem with this? Definitely, it will be in no conflict with any other exam or other material. So, Abbas Al-Yahya, are you with us? Abdul Karim? Ahmed Al-Hussein, Dawood Al-Haji, Hussein Al-Yusuf, Usama Shah. I just want to make sure that I did not see you checking it, so I just want to make sure that...
I don't know where it is, Doctor.
So at least Hussein, I know that it's fine with you. Usama already has raised his hand. Abbas Al-Yahya, you can either raise your hand or check the yes mark. Okay, and Abdul Karim, you said it's Abdul Karim, is that fine with you?
Yeah, I'm here.
Fine. So, and Hussein Yusuf, you said it's so fine. So we are going to meet. I think we have maybe someone is missing today. Actually, 2. So we need them. I'll compare the report sheet of the attendance of this of the class with the class roster to know who's missing. But we need to make sure that everyone knows that we are going to log in at that time. So it will be 8 o'clock on Wednesday, inshallah. I'm going to post the book. So please, today, sometime after maybe half an hour from now, you can check and find it there. It's a PDF file. The size is a little bit big. It's about 25 megabytes, but you should be able to open it easily, inshallah.
Doctor.
Yes.
Can you upload the solution for quiz 2 for any version?
Oh, for quiz 2, fine. I'll pick up one version and I'm going to solve it and put it in detail so that it becomes self-explanatory. And hopefully for any version which is different than that, you can just put your number in and then you're going to have the correct answer. Yes, I'm going to do that today, inshallah.
Thank you.
دكتور معلش عندي سؤال.
Yes.
بالنسبة لو طلب مننا التي فور اير كيف حنطلعه؟ زي سؤال الهوم وورك.
الهوم work you have ES, or you have if you look at the internet and you Google for psychrometric calculator, you will get something where you can get it from there. You are sitting at home, you have your time so that you can look for the property. This is something which is not there in the exam. So in the exam, I can ask you for the temperature of water, but not the temperature of air.
Okay.
I would provide you with a link to a software you get into the internet where you, for example, you put the value of H and you put the value of either the relative humidity or the humidity ratio, and then the software will be giving you the value of T, which doesn't make much sense if I'm talking about an exam problem. Okay, so inshallah we'll see you on Wednesday, ya shabab.
Oh.
Yes, Saleh, تفضل.
The figures for design HDH.
Yes.
They will be similar to the exam, or?
Yeah, they will be provided to you. They are the same figures, by the way, or something similar if the temperature is different. But more or less, it will be the same as you have.
So I can print it to use it.
You can print it, yes.
Doctor?
Yes.
Can you please upload also an exam and solve an example for the single effect evaporate?
Yes, I will. And you will find one in the book, which is given in details. And the example that we have solved, I can make sure I can post it as well.
Okay.
Inshallah. So sometime today you should be able to see it, inshallah.
Thank you.
Yeah, you're welcome. Okay, Shabab. So we'll see you on Wednesday, inshallah.